Okay, so I would like to go to, now today finally start electrodynamics. Now, the equations we have up to now, we know that the divergence of the electric field is 4 pi rho. No, the divergence of the displacement field is 4 pi rho. Curl of the electric field is 0. Divergence of the B field is 0. Curl of the H field is 4 pi over C times J. These are the equations we have. In addition to that, we know that charge is conserved. Now, we know the force law, the Lorentz force acting on a point charge. This is E plus V cross B. We know conservation of charge, del rho by del T, plus the divergence of J should be equal to 0. So let's look at the last one. The charge conservation. Well, we know that rho is nothing but 1 over 4 pi divergence of D. This is from this equation. Divergence of D is 4 pi rho. Plus the divergence of, well, J is 4 pi over 3 C. No, C over 4 pi. Curl of H. Yes.
Is the continuity equation valid for free charge only? I mean, can we apply this continuity equation for the free charge alone?
Well, I mean, yes, if you want, let's just go to vacuum. In vacuum. So all the charges are free. But now we have a problem. This should be equal to 0. But the last term is already 0. Divergence of a curl is 0. So we see that the del over del T, 1 over 4 pi, del over del T of the divergence of E should be equal to 0, but it need not be. So now there is one inconsistency in our equation. Now, it's not a big surprise that there is an inconsistency because these equations we had obtained in the case of statics. Nothing changes in time. So somehow we have to correct these equations. Well, the easiest thing to do that correction is, let's pick up that term, the great divergence of that term is 0. Let's add a term to that such that it will cancel the first one. And the easiest term will be minus 1 over 4 pi del E by del T. So if we add that term, then here we are basically adding the term. So here we have a 1 over 4 pi minus 1 over 4 pi, the divergence of dE by dt, and they do cancel. So basically that is one way of curing this discrepancy. Let's say J, before it was C over 4 pi, curl of B. Now we are adding this term minus 1 over 4 pi del E by del T. Or curl of B should be equal to 4 pi over C times J plus dE by dt, 1 over C. Well, of course, this will cure our problem. Will it be true? So that is something we need to check. That was, I mean, at least we know that this term cures one of the problems in our equations. Now let's look at another problem in our equations. Well, we will see that this we will call this the displacement field. Displacement current. Well, you can do this for the free charge also, free charge and free charge current, because the bound charges, they are already staying there, they are not moving anywhere. So they are already conserved. The free charges themselves should also be conserved. So if you just repeat the same derivation for elect E and for our fields in matter, you basically get the curl of H is equal to 4 pi over C times J plus 1 over C derivative of d by dt. This will be one of our equations. Now let's look at the other inconsistency in our equations. Now let's look at this problem. Let's assume we have this region of magnetic field. Now the other problem is basically related with the fact that our equations are not are frame dependent. We are talking about velocities. But velocity is a frame dependent quantity. So if you go from one frame to the other frame, then you might have some weird results. And actually this will be our weird result. Let's just assume that we have some kind of a circuit, some battery over here, some lamp. We have these wires running into the region of the magnetic field, and in this region we have this rod that is free to move. It will be always in contact with our wires. It's always in contact with our wires. Now we will set this rod in motion, let's say with a velocity v. Now let's just imagine one electron inside. So will there be a force acting on it? What will be the direction of the force acting on this electron? V cross P is upward, the electron has negative charge, so the force will be downward, so the electron will be moving downward. And hence there is a current moving upward. What is the force acting on the electron? It will be QV times P over C. This is the force. The total work done on the electron, let's say this has a length L. This will be Q over C VB times L. What is doing this work? Not the magnetic field. Well, if there is a force acting on our rod, it will be the external force that is doing the work. If there are no external forces acting on our rod, then basically the electrons will collide with this bound surface of the rod and extract energy from the rod. Basically, it's the rod doing the work on the electrons. And hence, if there are no external force, the rod will slow down. And the work per unit charge is 1 over C VBL. So we know that if we imagine 1 unit charge, let's say electron, it starts from this point, it will go down the rod and through our circuit. Well, okay, there is no battery in our circuit, sorry. It will go around our circuit and then come back, and so there will be light in the lamp. Now let's go to another reference frame, the one that moves. Let's assume that we are pushing the rod with velocity v, so that it will have constant velocity. So we go to this new reference frame which moves with velocity v relative to the initial reference frame. Well, in that new reference frame, well, v will be 0. The rod is not moving. So if the rod is not moving, there is no magnetic force acting on it.
The wires are moving.
So what will be the direction of the force acting on the wires? Okay, the wires are moving towards the left. So this is the motion of the charges. B is into the screen. So V cross B is the force acting on the electron will be upward. Well, the electrons cannot move upward because it's an infinitely thin rod. There is no up or down. The electrons can move left or right, but they cannot move up or down. And the vertical segment, which contains the lamp, is out of the region which contains the magnetic field. So there is no force acting on it, even though it is moving.
But here, the source of the magnetic field is going left.
Okay. So?
So I guess we can modify our expression for the force as the relative velocity between the rod and the source of the magnetic field.
Well, that is actually what we will be doing. So you see, in this form, where V is the velocity of the charges, this result depends on the frame. In this other frame, there would be no, since the charges are not moving, or the ones that are moving will not feel a force in the direction of the current, there shouldn't be any current if we stick with the description that V should be the velocity of the charges. So it will be a frame-dependent quantity, and we get inconsistent result with different frames. Well, the easiest modification will be just to define this V as the relative velocity. But then the problem is, how do we determine this relative velocity? You see, these magnetic B field lines are just our mathematical constructs. We are not measuring the B field lines. And these are just charges. The currents creating these B fields are at infinity. So we don't even observe them. So first of all, as your friend points out, we have to change this definition, this result, the W over Q. Yes, it is 1 over C V B L in one reference frame, but we should somehow modify it so that it will be valid in an arbitrary reference frame. Now, the second problem is, you see, again, just look at this electron, whichever frame you like. The electron feels a force in one reference frame, at least. It's feeling a force in the downward direction. So in the other reference frame, it should also be feeling a force that is in the downward direction. So because the force or the acceleration is kind of independent of the reference frame, at least in Galilean relativity. The acceleration should be independent of the reference frame. So if there's an acceleration in one reference frame, there should be an acceleration in all the inertial reference frames. But you see, in the second reference frame, V is 0. In the second reference frame, V is 0. So basically that tells me that there should be an E in that reference frame, the electric field. So what creates this electric field? Well, there are no charges nearby. You see, the charges creating our magnetic field, we said that they are at infinity. There are no nearby charges. So this new kind of electric field is not created by the charges. It should be created by the motion of the B field line or changing B field. So that's kind of our new source of electric fields. Now, let's go step by step. Let's start with this one, with this expression over here. Now, what is this? This work per unit charge is what we call the EMF. So this is actually the EMF. The battery has an EMF. So we will see that changing magnetic fields creates an EMF. In this case, it will be the moving rod that is creating the EMF. That it is basically the work done on a charge as it crosses our system. Now, let's say this distance is x. So in this example, at least, V is nothing but minus dx by dt. Minus because we define V to be the magnitude is positive, and with that choice of the direction of V, x is changing, x is getting smaller with time, so dx by dt is negative. So this tells me that EMF can be written as 1 over c d by dt minus of x times b times L. Or let me just call this distance my x from the edge of the region which contains the magnetic field. But you see, this is nothing but minus 1 over c d by dt b times x times L is nothing but the area in my loop which is subject to this magnetic induction field. And this B times A is what we define as the magnetic flux. B dot dA. Now, the change in flux basically can have two origins. Either the B field is changing or the area is changing. So the claim, which has to be tested by experiments, is whatever the source of the change of this flux, EMF is always written by minus 1 over c times the rate of change of the flux. Again, as I repeat, it's not a derivation, it is a claim. So whether the flux changes because of a changing magnetic field or because of the changing area, this law should always be true. Well, if that is the case, so let's just consider a region in which the B field is changing, and let's just assume an area that is fixed in time. Well, in that case, the EMF, the work done on a charge, is basically due to the electric fields. Magnetic field cannot do any work. So this EMF is nothing but E dot dl over our closed loop. Then this law tells me that E dot dl should be equal to minus 1 over c d by dt times B dot dA. Remember, this integral is over some area A, and this E dot dl integral is over the boundary of A. Now let's take one more step. The loop integral, the integral over a closed loop, I can convert it to an area integral. It's just the curl of E integrated over my area. This should be equal to, now I am assuming an area that is fixed. So the area doesn't change, it's not moving. So the time derivative, the time change is only due to the changing magnetic field. So I can move that time derivative inside my integrand. So it is minus 1 over c over the area del B by del T. B field can depend on the position, so that's why that total derivative with respect to time now becomes the partial derivative with respect to time. Well, since this is true for any area, the curl of E has to be equal to minus 1 over c del B by del T. Well, in fact, this is why B field is called the magnetic induction field. It induces the electric field. Now, of course, we started from a simple system. Just a rod, a rectangular circuit, etc. So can we generalize it to some arbitrary region, arbitrary loop, moving in a magnetic field, in a constant magnetic field, let's say. So you say that if you just consider our steps, we considered some circuit, some loop, in a constant magnetic field. And for this constant magnetic field, we show that the induced the EMF created by the motion of this our circuit is given by the negative time derivative of the magnetic flux going through my circuit. Of course, this change was due to the change in my circuit. And then we took a big leap. We claim that this relation holds even if the flux changes due to a changing B field. That was the assumption. It's an assumption that should be tested by experiment. We didn't derive it. There's no derivation for that. It should be tested by experiment. And when we do those tests, we actually can verify that whatever the reason of the flux change, it can be the change in the area, the change in the B field, or both, the induced EMF is always minus 1 over C times the derivative of the flux. Now let's try to, at least we can just lift one assumption that we made on the way. We just assume some rectangular loop. Let's choose an arbitrary loop in a region which contains some B field. And let's see what will be the can we actually prove that the EMF is equal to the change in the flux for this loop? Now this loop will be changing in space. So let's say we take some segment over here, dl. Now it will be displaced in this direction. Let's call the velocity of that point v. At that point, there is an induction field B. So the force acting on our charges will be Q times V dB, V cross B. And well, the charges, there will be a work done on the charges as the charges cross this region dl. And that force, this is the force, that work will be just Q, V, B, V cross B times dl. Hmm? 1 over C. So dW over Q, the work done on a unit charge, as it crosses this region, this is the contribution to the EMF, will be just V over C cross B times dl. So total EMF will be the integral over the loop of V over C cross B times dl. No, it's not a vector. Yes, you are right. So let me ignore this one for the time being. Dot dl. Yes, it's a vector now. So dW by Q is equal to V over C cross B dot dl. Which direction? Well, I don't really care, to be honest. You see, when we are defining this EMF, we said that EMF is E dot dl. It can be both positive or negative, whichever direction you choose. So I will choose my direction to be this one. EMF, as I said, it can be both positive or negative. So let's say we wait a time dt. In a time dt, this segment will move this much. The change in flux will be, let's say, the B field at that point times dA. This is my dl. Now dl is in the other direction. So this will be equal to B. Now what is dA? Well, dA vector, I can just define it as dl cross V dt. This is my area vector. Or this is equal to d phi by dt is equal to B dot dl cross V, which is equal to dl dot V cross B do you agree? This is nothing but 1 over C. Now this is C times d epsilon. Well, let us also, you see, dA vector is out of the screen. Should be out of the screen based on our choice of dl. Right? But dl cross V is into the screen. So there should be a minus sign over there. So here I have a minus sign. So here there's a minus sign, here there's a minus sign. So there's a minus sign over here. Or let me just use this notation. Why I change that? Because it's the change in flux for a very small area for a very small amount of time. So that's why it's the double small. So that tells me that d by dt of d phi is equal to minus c times d epsilon, which is basically the end of my proof. You just integrate both sides. You get epsilon is equal to minus 1 over c times d phi by dt. The integral of d phi gives me the total flux phi. The integral of d epsilon gives me the total epsilon.
What exactly do you do?
You see, we started from here, and we, in this example, in this simple example, we show that epsilon is minus 1 over c times the rate of change of the magnetic flux. It was a special case of a circuit, a rectangular circuit with a rod moving in a uniform magnetic field.
Well, this is just based on a thing.
This is any loop, any magnetic field, not necessarily uniform. So whatever magnetic field you have, whatever kind of loop you imagine, if the magnetic field is not changing in time, at least, so this is the case we are studying, if the magnetic field is not changing in time, but your loop changes its shape. It can be translated, it can be deformed, whatever the shape you have. And even in this case, the induced EMF due to this change in the area of our loop is given by minus 1 over c d phi by dt. whatever is causing this change in the shape, whatever the change you can consider, this relation always holds. Now the next step is the assumption, is the hypothesis, let's say, that even if it's not the change in the shape of the magnetic, shape of the circuit, but due to the change in the B field, this law will still hold. And this hypothesis is tested by experiment, and it's verified by experiments. And hence, this equation holds whatever the motivation for the change of this flux going through our area. And this basically tells us that the curl of E should be equal to minus 1 over C del B by del T. So this is one correction to our equations due to time-changing effects. If B is changing in time, then we have this correction in our equations.
I can see this from one of the expressions above, but how do you relate EMF to this?
Well, the relation is basically here. EMF is the work done on our charges. So I'm just saying, I'm assuming a loop which doesn't change in time. So it's the magnetic field that is only changing in time. So if there is an EMF created, it should be due to the electric field. And the EMF around this loop is nothing but the integral of the electric field around this loop. So I have this relation between the EMF and the electric field. And the magnetic flux is defined as the integral of B around an area. So once I have the relation between the EMF and the rate of change of flux in a changing B field, I can just put in the definition of the EMF in terms of the electric field and the B flux in terms of the B field, and it leads me to this law. You see, before we said that, okay, the curl of E was equal to 0, so if we integrate the electric field around any closed loop, it should be 0. But now we don't have that condition anymore, because the curl of E is no longer 0 if the magnetic field, the B field, is changing in time. But that also brings another problem. If the integral of the E field around the closed loop is not 0, then the E field is not a conservative field. We cannot define a potential corresponding to our E field. Well, we will see that we can still go around this problem. But, I mean, kind of the potential loses its energy meaning. Electrostatic potential will not be, there won't be a one-to-one correspondence with energy.
My question is about area. I change of area. Does it mean change of the differential element of area or total area? For example, my area is constant, but the shape of the loop may change.
I mean, you see, that just brings a condition on possible values of dLs. But here I didn't use that condition anyway. So I just assume one part, it is changing, that this segment dl is changing, and so that there will be a contribution to the EMF due to that segment, and the flux will be changing due to that segment also. So, and the contribution to the EMF from that segment is related to the rate of change of the flux due to the motion of that segment. That is what I proved. Of course, there might be some other segment moving in some different way, such that the change in the area might be changing. Might not, the total area might be constant, but I'm not making any assumptions on that. if the B field in both of these segments are the same, if the flux is, the change in flux is the same due to the motion of both of these segments, then the total contribution to the EMF will be zero, but so what? Question?
We are trying to say that changing to the magnetic flux causes electric field, right?
Yes.
Is the same for the electric field, and changing electric flux creates a magnetic field.
That is what we will be, that's actually true. You see, okay, we didn't stress it that much. We will go back to that point later on. Oops, where was it? You see, if you look at this equation, which we claim should be true, if we want to have conservation of charge consistent with our equations, so this should be satisfied. So you see, even if J is zero, there might be zero currents everywhere. If there is a changing electric field, B cannot be zero. Or if the displacement field is changing somewhere, even if J is zero, then H cannot be zero everywhere. So the changing D field will create a changing H field, and changing B field creates an E field. So in that sense also, these equations for E and B fields are quite symmetric in fact. They are so symmetric in fact that it's kind of puzzling why we lose that symmetry in monopoles. We have electric monopoles, we don't have magnetic monopoles. Why is that symmetry lost? Everything between the E and B fields looks so symmetric. E and B fields? I don't know. Will they be? Well, let's see. I have a current carrying infinite wire. There's a point charge over here. Now the B field is in this direction. The electric field is spreading out. It's a static problem. So the E and the B fields are not perpendicular everywhere. So how can we prove it? We need to prove it. I mean, you might have this hunch. You have a claim that they have to be perpendicular to each other. Now then the question is, how do you prove that?
In what case are we expecting that they will be perpendicular?
In which cases? Well, that's another question. At least I have one case in which they are not perpendicular. He claims that there should be some cases where they are perpendicular. So what are the conditions for them to be perpendicular? Well, in static, they are definitely not necessarily perpendicular. But your friend claimed that the E and B fields created by each other should be perpendicular to each other. So how can we put it in a more concrete form? Now, I'm not expecting an answer right away. So we should better study first the consequences of this equation also. Why? So is the curl of H perpendicular to H? Is it? So if curl of...
A vector cross another vector, the resultant vector must be perpendicular both.
But this is not an ordinary vector, it's a derivative.
Vector is a vector.
Well, it would be nice if that was true all the time.
Consider if we have a constant.
Okay, I'm not expecting an answer right away. Okay, so think about it. So there will come a time when you will be able to answer that question. Maybe the final time, who knows? Okay.